All right, any questions? All right, let's move back just a little bit in terms of what content you've done. Oh, good thing I wrote that out there. The lab on Wednesday. We can do an open-ended one, which deals with some rotational motion, or we can do a more prescribed follow the steps kind of thing. You had expressed an interest in redeeming yourself. Do you want to do open-ended or more prescribed? What do you think your mood on Wednesday will be?
I personally prefer the more prescribed one.
Yeah, I think that might be where I'm leaning. I don't know.
Okay. And my understanding is we do have class next Monday. Thanksgiving break starts on Tuesday. Is that your understanding as well?
I think so.
Okay. All right. So we have a slinky, obviously. The rubber band is around it in case it falls off, because the spring constant depends upon how many coils I have here, and if if it falls off and I don't have a rubber band around it, then we're starting from scratch. So. I have tape on the bottom of it so that the motion sensor can pick it up. All right, so we've done some of this already, but first thing we need to do is figure out what is the spring constant. So we will just add masses, which are not here. They've been sitting in this room for months. All right. Apologize. Thought I had everything. All right, so we're going to add masses and see how far it stretches. We do need some sort of base, as in when nothing is on it, how far does it stretch? Don't need the motion detector quite yet. I'll use the table as my reference. And it is shaking, but 36.7 centimeters. Position. I said 37.7?
36.7.
You think?
36.7.
And then with nothing attached. All right, I'm going to add a 10 kilogram mass, or maybe 10 grams. Now I was hoping to have it perfectly centered right there so that it will all go down the same amount, but it is sort of tilted like that. So what I'm going to do is instead make it more obvious, then measure the high and the low point, and then we'll just take an average for the position. So the high point is, let's see, there we go. It's oscillating between, it's like 33.7. To, actually that's the high point, so 33.7. And this was with 0.01. Now, typically, if this were a real lab, we would not be trusting the manufacturer, but for right now, we'll just trust the manufacturer. And then the low point calm down. 31.8. So we get an average of 32.65. Try that one again. So we have a difference of 1.9. So adding 9.5 to that. So 32.75. Is that right?
Yep.
Okay. Is that a 20-gram mass? And as you would expect, it does stretch farther. As a matter of fact, ideally, it would stretch twice the distance, but we will find out. So the high side is 29.3. 29.3, and the low side, trusting that you will remember this stuff, is 26.4. So 26.4 to 29.3. Is that what I said?
Yes.
And the average is
27.8285.
it's gonna come up close. So that's roughly 4, roughly 5. Okay. Do one more, and then we'll come up with our sort of estimate for the strength constant. We're at a 50. And not touching the tape. Excellent. The high side. So let's more still before I touch it. That's up there. So 25, no, sorry, 15.6. And the low side, $11.1. $13.785.
0.35.
13.35.
That's what I got, yeah.
Okay. All right. So we have enough data points right there that we can come up with at least a crude estimate of the spring constant. Remember that it is in equilibrium right here. We have the weight acting down. We have the spring force acting up. In essence, K delta X is equal to mg, or K is mg over delta X. Ideally, we would plot it, and if we plotted weight versus delta X, then the slope would be the spring constant, or properly, because we're determining the weight and seeing what the displacement is. If I did displacement versus weight, then we would end up with the inverse So dependent versus independent, we did the inverse of the slope would be the spring constant. All right, so Patrick, you're cranking through, are you doing each one individually?
I was gonna try to do a regression on this, but I forgot how to do that.
Ah. Not sure?
I kinda zoned out, I'm not gonna lie.
So if we plotted the points, that is mass, so if we did the, let's do it properly. So I have a displacement here, and I have mg down here. So my weight in newtons, 0.098, which is sufficient since we're not going for perfection right now. 0.196, 0.49. Oh, I feel like I'm off point. Yeah, no, that's right. So our displacement here. Well, actually, if we did the slope of position would work just as well as displacement if we're just looking for a slope. Working backwards, 27 to 25, okay. That works. And then this would be 20, 23.35. Oh. It'd probably be better. Because we want to use SI units to do this in meters. So point. So 0. Do you have a question yet? Still trying to figure it out?
I'm working on it.
Okay. So 0.49, 0.23. All right. Six.
Yeah, I think I got something.
Okay, what'd you get?
For the slope, I got 2.0732A.
2.07.
328.
328. I suspect that you did reverse of whatever is up here.
I have
Because all of my displacements are
Yes, I have weight as the,
As your Y.
yeah, let me just swap them real quick. Can you read out the X values or the delta X values, please?
The delta X values, I had 0.0395, 0.0885, 0.2335.
Thank you. Okay, this time I got 0.480685.
48065.
0.480665.
Okay. And what would be the units? That's meters and this is newtons.
Meters per newton.
Yep. All right, so because I plotted it this way with dependent versus independent, we end up with the slope is the inverse of the spring constant. And therefore, the spring constant would be, well, actually the reciprocal, which I'm guessing is somewhere around 2.07328 newtons per meter. And that is a lowercase k. All right, the other issue that we have is the fact that we've done a lot of stuff with ideal. The spring obviously has its own mass. So let's try to figure out what is the effective mass of the spring. And to do that, let's recall some of the equations that we've dealt with. Let's clear this. I know that omega is the square root of k over m. I know that omega is equal to 2 pi times the frequency. I know the frequency is 1 over the period. So sort of working backwards, therefore this is 2 pi over the period, which means that the period is 2 pi over omega, which is true for, if I can define something as in y is equal to some amplitude cosine or cosine omega t plus 5. 2 pi over omega would be the period. So from this, we're going to figure out what omega is, and then once we have omega, we can figure out what the effective mass is. So, if you would be kind enough to do timing, we'll time 10 oscillations as usual. Make sure that. Let me do my usual 3, 2, 1, go. All right, ready? 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did not put it back, I put it over here. All right, so what times did you get?
9.14.
I got 9.08.
Nice. Glad that we're in the same ballpark. So doing the fancy math, we get 9.11 seconds. So therefore, omega is 2 pi, back over here. 2 pi over 9.11. And so we get an omega of .6 something, probably 0.69 something,
689.
0.689
6897.
units.
Meters per second.
Not for Omega.
Radians per second.
What'd you say?
Radians per second?
Yeah. All right. So we know what omega is, we know what K is, and let's write that off to the margin over here. 2.07328 newtons per meter is K. And then forgotten already, 6897 radians per second is omega. So let's figure out what the effective mass is then of the spring. So omega is the square root of K over M. So omega squared is equal to K over M, or M is equal to K over omega squared. Five-ish. 5 pencil.
I got 4.35.
4.35.
8.
Let's make sure our units are working out here. So omega is, oh, what's the period? It's not 9.11 seconds.